This is part 2 of analyzing function graphs, and we're still working on finding x and y intercepts. Here we have another piecewise function, and we're looking for the x-intercepts. So we can recognize that it's crossing the x-axis at this value. It's also crossing the x-axis at this value. So we need to approximate those particular values. So this is at approximately negative 4.5. And then the first value here is at approximately 1/2. You could write that as 0.5 if you prefer. And remember, we can write intercepts as ordered pairs. So negative 4.5, 0 would be one ordered pair, and the second one would be 1/2 or 0.5, 0. Also, we want to look at the y-intercept. So we see there is one of the y-intercepts, which is at positive 3. So the y-intercept is at positive 3, which as an ordered pair would be 0, 3. There are possible graphs that will not have x and y intercepts, and in those cases we would write none for the x and y intercept analysis. Now let's look at roots and zeros and solutions. When a graph is graphed and we're looking at x-intercepts, we know the x-intercept as solutions for the graph. But solutions can also be called roots, zeros, or x-intercepts. So it is important that we know these vocabulary terms are the same or indicate the same values. So when we're looking at a solution or a root or a zero for this particular graph, we are looking for its x-intercept. And its x-intercept is at negative 1. So we would say negative 1 is also a zero or also a root. We will look more at roots when we get into polynomial functions, but for now, we'll just focus on linear and absolute value ones. Intervals of increasing, decreasing, or constant. When we're looking at a graph, we want to look at how the graph is shaped and how it's going. So some basic things that we should remember is that we always read a graph from left to right. We've talked about that before in class as we've looked at graphs, but it is important that you have that in your notes and you know that. We also want to use the x values when we talk about intervals of increasing or decreasing. So when we talk about it, we'll say a graph will be increasing when the x values are getting bigger or larger when the y values are also getting bigger or larger. Now, not only do we say larger, but we say that they are approaching positive infinity. So keep that in mind as well. A graph that is decreasing means that the x values are getting bigger or larger, which would be going to positive infinity, while the y values are getting smaller or going to negative infinity. If a graph is constant, then the graph is horizontal. So as the x values get bigger, or larger, whichever way you want to say that, then the y values will stay the same. Now, let's look at some graphs to talk about increasing and decreasing. So again, we're looking at this absolute value graph. We're going to read it from left to right. So as we follow this graph, we see that it's going down first, and then it switches and starts going up. So we're saying from left to right, since this graph is going down in this region, let's look at what x value it goes to. That is -3. So it decreases from -infinity to -3. And then at -3, it switches and starts rising. So that's increasing. So from -3 to positive infinity, the graph is increasing. End behaviors means we look at the very ends of the graph, not what it's doing overall. So every graph has an end behavior, and they usually have two ends. So when we're looking at this particular graph, we see that down, each end is pointing down. So we talk about the end of the behavior. As the x values go to -infinity, we can see that from the x-axis, that the y's are going down, and so we call that -infinity. Then on the right side, the x's are getting bigger, so they are going to positive infinity, while at the same time, the y's are still going down, and so that is -infinity for the y's. Most functions have a critical point of some type on the graph, and we've talked about the vertex on the absolute value graph as being a critical point. So we also want to be able to find the vertex of an absolute value graph. We've talked about the C and the D value also meaning the same thing for H and for K, and that's what we use for the vertex. So as we look at this equation, this value here, -3, represents the H, and the value 1 represents the K. We do want to take the opposite of that value. So that means our vertex is at +3, +1. We can always use the graphing calculator to check that particular point. Now, last, we want to look at analyzing a particular graph, all of the 5 characteristics that we have talked about in order to look at a particular graph. So we start with the equation, y equals the absolute value of x plus 4 minus 3. So let's talk about first, where is the vertex? So the vertex for this particular graph is the opposite of the C, or the H value, whichever you want to call that. So that makes it -4, and the y value is -3. So we can use that particular point as a value to start our graph with. So let's mark those units off. And I know the location of the vertex. Now, from our practice in graph with transformation, I know that this graph has shifted to the left 4 and down 3 based on its equation and its transformations from the parent graph. The value of the slope for the linear equations is +1, so I know this graph is going up 1 and over 1 for each side of its particular V-shape. So, if I was going to look at analyzing this particular graph, I might want to start with the x and the y intercepts. So for the x-intercepts, I could look at this graphically and see that this graph is crossing at -5 and at -3. The y-intercept is looking at approximately, based on equal units, around +4. What would be a way that I could check this numerically to find out for sure? I could plug in 0 for the x. So if I plug in 0 for the x and check that, maybe I can get a more accurate answer than my estimate. So I see that I have the absolute value of 0 plus 4, which is 4, and 4 plus -3 means that this graph should be crossing at -1. So apparently my scale is a little mixed up on this particular graph. So let me mark this out and put -1 for that y-intercept. So we've looked at the y-intercept, and we know that also the zeros, or the solutions, should also match the x-intercepts. So my zeros for this particular graph are -5 and -3. If I want to analyze how this graph is increasing and decreasing from left to right, I see that the graph does go down first. Left to right, it's going down to the vertex. So that means that as x is getting smaller, or excuse me, going toward positive infinity, the y's are going down. And then it changes and starts increasing. So we want to give the interval for which it is increasing and decreasing. So let's do the left side first. It is decreasing from -infinity to -4, which is where the vertex is on the x-axis. And then this particular graph starts increasing, and that is from -4 to the x value going to positive infinity. Last but not least, we want to talk about the end behaviors. And so the end behavior for this graph, we look at the two sides. We have the left side and we have the right side. On the left side, as x approaches -infinity, it's going up. So we say the y's are approaching positive infinity. Then on the right hand side, as the x are getting bigger, so they are approaching positive infinity, we'll say that the y's are also still rising, so that is approaching positive infinity.